Hi guys, welcome to part 2 of all you need to know about switch mode power packs to fix stuff. I hope you watched part 1, I hope you enjoyed part 1, and it was quite a long video, but there was a lot to learn in there. So I split it in two, like I've split these power supplies in two, and we'll put the other 5 repairs on this one. So in this video we're going to do some practical repairs. We're going to look at all these power supplies, see what is wrong with them, see if we can fix them, and have a look how the circuit varies from the one we had in the previous video. And then we're going to have a look at the way the feedback system works and how to test whether the feedback is working. This is the circuit that regulates the output voltage. So that's what we're going to do in this. But first of all, I just want to have a quick chat about something I mentioned towards the end of the last video. This is our basic circuit diagram with a little addition on it. I'm just going to zoom down on it. What I mentioned towards the end of the previous video is the current sense resistor. So this is a low value resistor, typically maybe 0.5 ohm to 2 ohms, found on the primary side of the power supply. And I've actually drawn it on the diagram now, but lost this bit of recording on the end of the last video. So we'll do it now. The current sense resistor actually goes here. So it's from the MOSFET to hot ground. When this MOSFET is switching current through the primary, I hope you can see that the current which flows through the primary of the transformer is the same current that then flows through the MOSFET, either internal in the switch mode power supply controller chip or an external one to the chip, and it then flows through the resistor. The controller chip then can monitor the voltage across this resistor. The controller chip itself is connected to ground, of course. It has a connection to hot ground already. So it only needs to connect to this end of the resistor. And it monitors usually on a pin called CS, current sense, but it could have a few different abbreviations. The more current that flows through here, the higher the voltage, and this can be set to effectively switch off the pulse width modulator and therefore switch off the MOSFET, internal or external, if that current is too high, if the voltage here is too high. This also effectively monitors the current on the output, because any current drawn from the output will cause this pulse width modulator to drive wider pulses to effectively pull more current through the MOSFET here on the primary side to effectively deliver more current to keep the voltage correct. So measuring the current sense here actually effectively also measures the current on the output. A couple of things can go wrong with this. The resistor itself can go open circuit. If the resistor goes open circuit, then effectively the thing can never start. There's no current path down here. There's sometimes other resistors in the network, and if one of those goes high in value, these low value resistors don't tend to, but they could go high in value. If the resistance is too high somewhere in the circuit, this will think there's more current flowing than there actually is. So you can get a kind of a false flag situation where it thinks there is an overcurrent and shuts down even though there isn't. One other thing I'll mention about this resistor: if you have a short circuit MOSFET, it's very likely the current has also blown this resistor as well. So this has gone open circuit. So it's worth looking. If you find a short circuit MOSFET here, is there a current sensing resistor? They're quite easy to spot. They're normally near to the MOSFET, and it will be a low value resistor. This one I think is brown black gold, which is a 1 ohm resistor. So that would be the current sense resistor on this one. So once you find a shorted MOSFET, have a look for a resistor like that, low value, and just make sure it isn't open circuit. Or for that matter, make sure it doesn't read a higher resistance than it should do. Yeah, look at the markings on it. Let's just have a quick chat again about these large capacitors. These are the capacitors which charge up to about 320 volts when you apply power to the power supply. And that is generally not a problem as long as you don't poke your fingers in here. But the problem that can occur, depending on the nature of the fault with the power supply, is there may be no discharge path. So when you disconnect the mains, the capacitor cannot discharge. So in that situation, how do we make it safe? We need to discharge the capacitor ourselves. So the first thing we need to do is to check if there's any voltage in it. I can get hold of this side of the power supply. This is the low voltage side, so all this is safe anyway. What we need to do is first is to check if there's any voltage in the capacitor, and that's quite simple to do. We just use the voltmeter. So we'll take our voltmeter on volts range. There we go. We'll measure directly across the capacitor, so we just see where that is. Yeah, that one's here, and we can see if there's any voltage. I mean, this has not been switched on since yesterday, so there is no voltage. There's two ways to discharge the capacitor safely if you find there is some voltage in there, or two main ways. One would be to leave it, for some hours and then measure again. But if you don't want to wait, and assuming you want to discharge it yourself, the way to do it is with a power resistor. So this is a 3.3k 5 watt resistor. The value is not critical. Anything from about 2k to about 5k is fine. If you use a higher value, it might take too long to discharge, but it will discharge. If you use a very low value, you're going to cause a spark and a flash. So anything like this, a 1k resistor or something, will be fine. And to discharge it, quite simply, you just hold the pins of the resistor against the pins of the capacitor on the circuit board. So you literally hold it on there for about 5 seconds, and that will discharge your capacitor. You can then double check by just coming in and measure it again. If there's still too much voltage in, you just come along again and discharge it. What you should not do is use a screwdriver or something similar and just short the capacitor out. It will certainly discharge it, but suddenly discharging the capacitor like that is very bad for the capacitor. It can damage the dielectric, which is the insulated layer inside the capacitor. It's not good for your capacitor, it's not good for your tools. And if you're going to do this, by the way, ignoring my warning, don't hold it like that, hold it on the insulated end, yeah. But that is not the way to discharge a capacitor. Neither is this way, to use a pair of long nose pliers and short it. It's just as dangerous. You get sparks, which are basically little bits of white hot metal that can end up in your eye or in some other orifice where you didn't really want it to be. And also with this, again, you can be very careful because your fingers can slip onto the conductive part of it and you can get a shock that way. So that's how to discharge them. Another quick point I will make is there's often a heat sink on the primary side of the transformer here and here. This heat sink is often connected to hot ground. Now, if you have a plug like this, which will go in either way, this could either be connected to hot ground, the negative end of the capacitor, or it could be connected to the live, yeah? I mean, hot ground doesn't necessarily mean it will be in the neutral of your power lead. It could be on the live of your power lead. It's AC, the power supply doesn't care. If you touch it, you will care, yeah? So don't touch these heat sinks, at least until you've discharged the capacitor, and don't try to pick it up by the heat sink while it's running, yeah? It's not ground, it's not safe. Okay, so now we've had a second little chat about the dangers. Let's get on and look at one of these power supplies and see if we can fix it. Now let's look at some faulty power supplies. This one is a 5V 2A. I think it was dead. We can just check that to see if that's the actual problem with this one. It has been plugged in before, but I guess we might as well just check for short circuits on the output first before we try it. Here we have the meter on resistance range, so we can have a quick look on the output just to see if we have any short circuit here. Okay. No, it's charging the capacitor, so we're seeing the capacitors here charging up. So there's no short circuit. We can have a quick look while we're at it. Is there a short circuit on the input? If we measure across the main capacitor, that's a good place to do it. Now, this is not being switched on for a few days, so it is safe. But normally you would have to just check first to see if there's any high voltage in the capacitor. So let's do that anyway, because it's good practice. So we'll just go to the volts range, and the main capacitor, so you can see it down under here, the two legs, and that is going down, yeah, it looks like it's coming somewhere here. Just see if I can see again where they are. There's a lot of glue on it, which makes it a bit hard to find. If I can't find it exactly where it is, another good place to test for shorts is on the output of the bridge rectifier, which is here. So let's check here. So with the bridge rectifier, we have two positive ends, two negative ends connected to each other. Let's see which way around this is. So we need to find two cathodes which actually connect to each other. And we need to put it onto resistance to do that, of course. So let's see if we find the positive output. Yeah, so those two cathodes connect to each other. So the other end would be the negative, which is two of the anodes. Do these two connect to each other? Yes, they do. So that effectively is the output, and we can just measure across the bridge rectifier, and we don't have a short. From here, actually, we can easily find out where the pins of the capacitor are. So from the negative output of the bridge rectifier, we'll go to the negative end of the capacitor, wherever it is. And it's there. That's the negative side of the capacitor. So I'm pretty sure the positive side of the capacitor is going to be here. And this would go to the positive end of the bridge rectifier. If we just find it, that was here. Let's see where this goes to. Yeah, it goes there, exactly where I thought it was. So your main capacitor is wide across here to here. Now we know where it is. And we know there's no short, and we know there's no high voltage in it. There's no short there. And there's no voltage in it. Let's plug this in and let's see what the actual fault is on this power supply. So I'll just rest the PCB back in here. We'll connect to mains lead, and then let's see what it's doing, or let's see what it's not doing, more likely. Okay guys, we're ready to go. I have the camera pointed at the light bulb here. So on a power supply, you'd expect it with no load, effectively, for that light bulb to flash once and go out, or come on dim once and go out. And that's because the main capacitors are charging up. But with a small power supply like this, especially with no load, it might not light at all. It doesn't mean that the mains power hasn't got into the power supply. So let's switch this on, and the bulb didn't do anything, like it was drawing no current. And let's see if we have any output voltage. Okay, so I'm just measuring across the connector, and this power supply is dead, so there's no power coming out of it. I'll switch it back off. Now let's have a look to see, is there any voltage in the main capacitor. And I can easily check by measuring across the bridge rectifiers we were just looking at. So we're on volts. So I can go to the negative end of the bridge, which was here, and the positive end of the bridge was here, and I'll get where you can see it. And in fact, this appears to have no voltage in it. Yeah, no voltage. Let's take it out and let's measure directly across the main capacitor. Now we know where it is. So the capacitor was between here and here, and there's no voltage there, there's nothing. Okay, so it's like there's no power getting into this, like maybe it has a completely open circuit connection somewhere, because what should happen, even if the power supply doesn't start, is it should charge up the main capacitor, which is this. So if this part of the circuit is intact, from the live to the bridge rectifier to the main capacitor, this should charge up to about 320 volts regardless of what is or isn't working after that, if there's no short, and there is no short. So let's have a look to see, is there a fuse maybe? So we can see, I'll just disconnect the power lead, because it was switched off and unplugged anyway. Let's see, so the mains comes in here and here. Yeah, this is where the power's coming in. You can see either side of this. So this is where your power comes in. Well, it looks like there's a fuse there. That's what it looks like. It looks like there's a fuse here. Yeah, and the fuse is blown. So let's remove the fuse first. This is why there's no power getting into the large capacitor. So let's remove the fuse first. We'll do this with a bit of solder braid, I think. Save me putting the vacuum desoldering tool on. A bit of flux, of course, is going to help. So that's one end of the fuse. That's the other end of the fuse. So we can get a bit of leaded solder on here, and then we can desolder this, I would think. Okay. Okay, see if that fuse will come out of the PCB now. So that's this one. If I unsoldered the right place, of course. Okay, so this is one end of the fuse. This is the other end of the fuse by the looks of it. See if that actually lift up. No, I'm not in the right place. Oh, yeah, it looks like that might not. Yeah, this isn't one end of the fuse. This is one end of the filter inductor on the input. The other end of the fuse is actually there. So I'm actually on the wrong place. Easily done when you're working on stuff like this. So let's go to here. Does that mean the fuse is gone or not, or was I measuring in the wrong place? Let's have a look. Let's have a look and see. It's coming out now, so it's coming out anyway. Yeah. Let's have a look and see what we've got. Yeah, there's what I think is a fuse. Looks like a fuse. Does it read like a fuse? It reads open circuit. Okay, so if that's a fuse, it is open circuit. You're just seeing a bit of resistance from my fingers there, actually. Yeah, that's open. Let's get this bit of heat shrink sleeving off. And let's have a look to see what this actually is. But I'm confident it's a fuse. Let's see. Yeah, it's a fuse with bits of wire tagged on the end of it. There you go. So that's our fuse, and it is open circuit. Now we know where the fuse is, we can effectively work out the circuit. So the fuse should go to the bridge rectifier. We can test these diodes, and then we can check if we've got a connection from the positive of the bridge rectifier through the coil to the MOSFET. We can check the MOSFET, and then we can check that we've got a connection from the other side of the MOSFET back to the negative of the bridge rectifier. So that's what we're going to look for next. So let's do it. The positive end of the bridge rectifier we already found. Let's put it onto continuity mode. Okay, and in fact, let's go to diode mode so we can test the bridge rectifier anyway. So we have one diode here. Oh, and that is short. Yeah, we have a short circuit there. That's the first thing we have, a short circuit diode. How about this one? That reads okay. Yeah. How about this one? A bit hard to get at, but I tried. That might be short, but it's hard to get to the end of the diode. Yeah, it looks like those two are short, and then this one could be short as well. Well, I think we know why the fuse blew. That one might be okay. So it's difficult to get down there without accidentally touching that as well. I think the best thing to actually do here is to remove all four diodes and have a look. Before I do this, I'll just make a note of which way round they go in case it's not marked properly on the circuit board. Easiest way to do that is to take a photograph on the phone with all this modern technology we have these days, of course. Well, let's have a look. So we'll just get a photo of our bridge rectifier, and now I'll remove the diodes. I'll do this using the vacuum desoldering tool this time, just because it's quicker and a little bit easier. So we have two diodes here, and we can see this is one anode and one cathode connected together, so that's one of the AC inputs. The AC is coming through this inductor coil. The other side of that goes to here, which I guess links into this somewhere, probably a link or something on the other side of the board. And the other power in comes here through the other coil, and I'm guessing that comes back to here. Yeah, there's probably a wire or link just under there. In fact, you can see the wire link. Yeah. So that's the AC path, but we can check it in a moment. Let's go on there. So that's those ends, and then the other ends we have an anode and another anode. You can see they connected together. Yeah, you can see the track from this one to this one. So this is a negative end. This will go to the negative of the main capacitor, which will be here, and then the other two, there's probably a link again which connects them back together. So let's just get these out, and let's see if they are actually okay or not. I think I had a short. Well, there's certainly something short around here. Okay. Desoldering tool. This, if you don't have one, should be on everybody's shopping list, yeah. This makes life so much easier. That one just fell out. That one's going to fall out. and that one fell out. So we already have two diodes that just fell out of the board. One of them is just hanging in by one leg. And the other one, yeah, it's loose. There's the other one here. Nothing holding it in. Yep. So we have our four diodes, and they're marked on the board anyway, so we know which way around they go. Let's see how these diodes check out now. We're on the diode test mode. So let's see what we have. Well, this one is either open circuit or it's good. Yeah, that's reading nothing. So that diode is open circuit. Yeah, sorry you couldn't see it. It should conduct this way. Get into it. Fiddly little thing. Yeah, let's pick it up. So it should conduct this way. That's open circuit. That's a bad diode. So look at this one. Again, same thing. The cathode to the negative, anode to the positive. That's a bad diode. Is the meter working? Oh. Huh. Happens, yeah. Always check your meter if you think something's not right, yeah. Let's go again. What's this one doing? That's short. That's a short circuit diode. That's short. This one, just get onto it. Short circuit diode. So we know why the fuse is blown. This one, that one reads okay this direction. There should be nothing in this direction. So that is a good diode, but I would trust it about as far as I can throw it into the bin. Because if you've got two short circuit diodes and a bridge rectifier, you can be fairly certain the other two have had quite a bit of stress. So two read okay, but I don't trust them. So we have four short circuit diodes. Now, what we need to have a look is, do we have a circuit path now to the main smoothing capacitor? So that's here. This is the negative end, and I can see quite clearly that actually goes to the two ends of the diode here and here. This one being nearest the end, and that is the anode and the anode of that one, yeah. So we know we have a connection to there. We can literally see it from here to here to here. Yeah, I'll just put a bit of solder back onto the capacitor. There we go. The positive of the capacitor, which we can see is over this side, is here. This should go to the other two ends of the diodes, the cathodes. So it's the second one in, and it's the furthest away from me. So the second one in here, and the one furthest away from me, this is the second one in, the one furthest away, should connect together and should connect to this end of the capacitor. So they do, so there's some wire link somewhere that's connecting that together, but it's all connected. Now, from the positive end of the capacitor, we should go to the primary of the transformer. There. Okay. And then from the other end of the primary, it should go to the MOSFET, which is here. And the MOSFET, it should go to there. But we have a problem, as I noticed before. This is reading a high resistance, the transformer coil is. We can go back onto the resistance range and we can actually measure it. Okay. There. And that is wrong. The transformer primary should read very low resistance. We know this end of the transformer, which is a bad transformer, goes to this end of the MOSFET. This end of the MOSFET, this end of the MOSFET, and then the other end of the MOSFET should go back to the negative of the large capacitor, possibly via a current sense resistor. And it doesn't. So we have yet another open circuit component somewhere in here. So the other end of the primary, which is obviously open circuit, goes to the MOSFET, one end of the MOSFET. There, okay. And the other end of the MOSFET, which will be the middle pin. Whereas in the end, this will be the drain, this will be the source. The source will go back to the negative side of the main capacitor, which we know is here. Or is it the drain that goes to there? I had a quick look at this off camera because the layout's a little bit strange, but I've figured it now. So from the and the transformer's okay by the looks of it. From the positive side of the large capacitor here, it should go to one end of the primary, and we have a connection to here, okay. And then we also have a connection to here. So this is actually a secondary. The primary is from here to here, and from here should go to our MOSFET there on the center pin, okay. And then the other end of the MOSFET, which is here, should go to the negative of the large capacitor via probably a current sense resistor, which is what I'm reading. So that is the primary coil, and it's actually okay. The secondary coil is here, and this one will be generating the power for the controller chip, like we discussed in the first part of this video. So you can go and refresh yourself on how that part of the circuit works. We looked at it in depth. So that's what we have. So these 4 pins are actually on the primary of this. Well, no, 2 of the primary of this and 2 of the secondary on the high voltage side. It's just an unusual layout. They normally inline that way, which is what confused me originally. So I'm glad I worked that one out. It seemed a little bit strange. What we don't know at the moment is why did the bridge rectifier blow, and the main likely reason is that the MOSFET blew. So maybe the MOSFET went short and then went open. I'll just go to diode mode. It's not short, but I'm going to take the MOSFET off and test it first. If the MOSFET's okay, I'll put some diodes in. We'll connect it via the light bulb and we power it up. I mean, it is possible, you know, that the bridge rectifier could just fail. It's not unheard of, but it's more common that something else went short, which is why the bridge rectifier then failed. So we'll get this sort off here. Okay. And we'll do the same with the desoldering tool. With large components like this, sometimes you can't get the nozzle over the leg, which I think we can't here, so it can be easier to actually use the soldering iron and the desoldering tool together and do it like that. Didn't easily come on that one, try it again. Yeah, so that looks like I might have it. I'll just clean this so it doesn't clog up on me for the next time I want to use it. Yeah, it's okay, it's cleaned. I can hear it sucking very well, so that's fine. Now, there'll also be something holding this heatsink on. I can see a pin here. This looks like it's probably it as well, so we need to desolder this. And let's see if this will now come off. Yeah, see, those two will save a lot of work. This has a little inductor on here, so we need to replace that if we replace the MOSFET. Let's have a look to see if this is actually any good. Okay, here's the peak analyzer. We can click the leads on in any order we like, doesn't matter. Okay, 1, 2, 3, go. Yeah, so the MOSFET's good. It's possible that the MOSFET effectively switched on due to a problem with the controller chip. So if effectively the controller chip put a voltage on the gate, then that might be a reason why the MOSFET failed. We can probably just check that to some extent, and if we measure from the gate to hot ground, the negative end of the large capacitor, it shouldn't read open circuit. We'd expect to read some resistance here. So let's have a look. So this is the gate. So normally speaking, on these, that's gate drain source or gate source drain, but gate is that one, yeah. So we'll go on the gate here. Now let's have a look to see resistance to the negative end of the main capacitor. Well, yeah, it reads 100. You can't see it. It reads 190 k. So there is some resistance. So it's not floating. What's the resistance from here to the positive end? Just out of interest. Yeah, 260k. So there's some resistance. So it's not like it's floating the gate. We can see a resistance to the positive end of there and the resistance to the negative end. So what I'm going to do with this now is replace the MOSFET, fit some new diodes, and then we can see what will happen. These diodes are 1M4007. It's a very common diode. These are 1 amp diodes. 4007 is 1000 volts. 4006 is 600, 005 I think is 400, and so on. Down to 4001, which is a 50 volts. But if you buy a bag of 100 of these, which will probably cost you like €1, they will replace any of the types from 4001 to 4007. The other thing we need to replace is the fuse. So let's have a look at the fuse. We'll get into the microscope so we can read the readings. And let's see what this is rated at as well. Here is our fuse, and we can see 250 volts and what current T 2A. So it's a 2 amp. T I think is time delay basically, so it's not a fast blow. It's a slow blow 2 amp. So I'm sure we can find something suitable to put in there as well. Okay, this is physically larger, T2H. I'm sure it's a 2 amp. Yeah, I'm sure it's a 2 amp fuse. So we'll put that in. I mean, we can use it temporarily to fix it. It wouldn't fit in the case with this fuse. But if we get it working, we could soon buy some fuses of the correct size. But this will do for testing anyway. I'll just show you how to solder the wires onto this. I'm just using some old resistors which have stiff legs. They're fine for this. We'll just chop that leg off there, and then we can solder onto the other end. So we have a bit of a wire there. So we need to just effectively make sure the leg's a little bit clean, just scraping over it a little bit with the cutters. Okay. Now you'll find that the end of the fuse doesn't want to take solder normally. So we just turn it around a bit. So if we try and solder on the end of this, we get a blob of flux on. And you'll normally find that the solder doesn't want to stick to the fuse, so we can just try it. Well, this, it did actually, but if it doesn't, then what you need to do is just scrape away at it a little bit with this on the end, and then it will take the solder. So we have some solder on there. We need now to attach this leg. So that will solder quite nicely. Oh. And then, yeah, make sure it cools down before you move it. Blow on it a little bit. And there we have the fuse ready to fit, and then the diodes, that's just easy, yeah. Okay, that's replaced those then. One of the pads stripped off here, we're obviously soldering it, but it just connects to here. It's the two ends of these diodes which connected as a link to one of the AC inputs, so I just effectively bent it over and soldered it on. So we have that. Now I just need to replace the MOSFET, and then we can see whether or not this will actually work. I'll move the camera over so you can see the light bulb under here. It is set to current limit, yes, so we're connecting in series with the bulb. That will hopefully prevent anything very bad from happening if this has some other reason why the bridge rectifier diodes have gone short circuit. We can switch it on and let's see what the bulb does now. So if it lights up bright, we've still effectively got a short somewhere. Let's see what we get. Well, it didn't light up bright, so that's a good sign. It may be running now, we'll have to see. So let's just go to volts range. Let's get to the output of the power supply and let's see if it's now working. And we have an output, but it's low. Yeah. Oh, that's interesting. So that means I can demonstrate something else. So it's working, but the output is not good. Yeah. This should be a 5-volt supply, and we have an unstable output. All the capacitors here look okay. I can easily just effectively fasten another capacitor in parallel with these just to be sure. So I don't see any other bad looking capacitors, but there's something wrong with the feedback circuit or something like that. So we now need to investigate what else is wrong with our power supply. The problem with this type of fault is that you have a feedback loop. And when one part of the circuit is unstable, it's likely the rest of the circuit is unstable as well. So we know on this one that the output voltage is not stable, it's reading low and it's wandering around. Now if that's wandering around, it's because this is driving the transformer in an unstable manner. So effectively this is unstable. The pulse width is varying, therefore the output is varying. On the transformer, and if you watch part 1, and I hope you did watch part 1 before you're watching part 2, otherwise this is a bit like sort of watching The Empire Strikes Back before you watch The New Hope. Yeah, it doesn't all make a lot of sense. So assuming you've watched part 1, which please do if you haven't, this transformer, as well as powering the output, powers this secondary, which powers the chip which is powering the transformer. So we're in a loop. If this output is unstable, you can pretty much bet that this output is unstable as well. So this chip has an unstable power supply coming into it, so it makes sense the output is going to be unstable. So the instability is everywhere. The same here. This chip is the voltage reference to TL431. This should have a stable voltage on it so that the LED and the opto-isolator lights up at the correct voltage. But again, if the output's unstable, this is going to be unstable. Yeah, the brightness is going to be varying and the drive is going to be unstable. And the problem is you don't know what's causing the instability. Is it because the reference is not stable? Is it because output capacitors on here basically faulty, so it's just not stable? Is it this capacitor? It often is. That's effectively faulty, so it can't maintain a stable voltage here. Is there a problem with the resistor? Is there a problem with the chip? You don't know. And the only way you do know is to break the loop, basically, to force part of the circuit to be stable and then figure out what isn't stable after that. I'm going to show you two different ways to do this. There's no doubt other methods, and I'm always interested to hear what you guys think in the comments below. And I'm sure there'll be some very good suggestions of other methods. But this is the way I do it. So the first thing I'm going to do, and I'll show you this, is switch the power supply off, and we're going to put on here, on the output, a voltage using our bench power supply between there and safety ground, effectively connecting to this, the DC output. We're going to put a voltage in here a little bit lower than the rated voltage of the power supply. So if it's a 5 volt power supply, we're going to put about 4.5 volts in. If it's a 12, we're going to put about 11 in. Yeah? And then we're going to take our multimeter in diode mode and measure across this side of the opto isolator. And the transistor should be switched off. So on diode mode, it should just be open circuit. We're then going to increase the voltage here to a little bit above the rated output, say 5.5 on a 5 volt supply. And if all this circuit is working correctly, what we will see is when this goes a bit above the rated value, this transistor should switch on and we'll read a reading, probably a low reading on our diode mode meter. So that's what we're going to do. We don't require this powered up because in diode mode we're actually applying voltage itself, about 4 volts normally off a meter, 3.5 volts. So this transistor has got power from our meter and this side has got power from our power supply. So now I've explained what we're going to do, let's do it. To make this a little bit easier to do, I'm going to tag a few wires on the power supply, so I'm not trying to hold too many things in place at once. So first we'll go from ground and we'll find where that is. This is the ground, and then the output voltage is going to be here. Yeah, here, okay. So we can clip the negative from our power supply to the outside of this. It's not easy to get a good connection to the inside, so I'm just going to solder a wire from here, and this is where we're going to attach the positive lead of our power supply. So we'll solder a little bit of wire onto here, a little bit of fresh solder. Could have used a bit of flux, in fact I probably will use a bit of flux when I attach the wire, just make sure I get a better connection on it. Okay, a little bit of solder on the wire. So that's where we can attach our positive. Now we want to check what's happening on the output of the opto isolator, and the negative of our test meter needs to go to the emitter, positive to the collector in diode mode. It's easy to test which is which because normally the emitter will be connected to the negative end of the large capacitor, hot ground, and it's probably this bottom one. You could look up the data sheet, that's another way. Let me just see if I can probably do it from the other side. So this is the opto isolator, and one of the pins will go to the large capacitor ground. Okay, it's this one. Yeah, this one is connecting. Yeah, this is the negative, the large capacitor. We can see it there. So this one is the emitter. So we're going to attach a couple of wires on here, and then if we have it the wrong way around, it just won't work. We can just reverse the wires, it won't do any harm. So let's tag a couple of wires onto here, and then we can make the test. I fastened a couple of wires on here. I think the blue one is the emitter, but if it's wrong we can try it the other way. You can either use a couple of crocodile clip leads, or you can be lazy and just wrap the wires around the probes. Depends really if you've got any crocodile clip leads or not, I guess, and your frame of mind on the day you're doing it. Yeah, I do have crocodile clip leads, but let's try it this way. So that's our photo transistor connected. Now we need to apply voltage from our power supply. We just need to check the rating of this PSU. So This is a 5 volt power supply. I'll put the camera where you can see the power supply as well, and then we'll give it a go. We're ready to go. I have the meter on diode range. The leads connected, as I was explaining, onto the opto-isolated transistor. We have the black lead from the bench power supply connected to the ground on the output, the 0 volts, and we'll connect the yellow wire. So it's drawing about 20 milliamps, a little bit of current. It's stopped. Yeah. And the photo transistor is off, nothing's happening. Now I'm going to take the voltage up to a bit above 5 volts. Let's see if this turns on. Yeah, see it there? So I have a bad connection. I did get it. So it's about 5.1, 5.2, 5.3, 5.4, 5.5. Yeah, it's there, yeah? The transistor is switched on at 5.5 volts, yeah? And it's stable. Yeah, it's off again. I mean, at this point it's slightly on. It's off now. Let's come over to... Right, you can see at 4.9 volts it starts to conduct. Yeah? 5 volts. And that voltage is what's triggering the pulse width modulator to change the width of the pulses. And if we increase the voltage up, once it gets to about 5.2, the transistor turns fully on. So that is working okay, and it's triggering at the voltage we would expect. So that basically proves that this part of the circuit is working fine. Here we know when we increase the output voltage, it turns the transistor on, and it's stable, it's not wandering around. So instantly we've proved the opto-isolator is good, the TL431 is good, and all the resistors in between are good. Okay, so that's eliminated that lot. So why is our power supply unstable? Well, I mentioned before the most likely culprit is this capacitor, but let's see if we can prove it. So we'll now use the second technique and see if this will actually explain to us what the problem actually is. I've taken the wire off the opto-isolator. I was correct which way it was. This end being connected to the negative of the large capacitor. That was the emitter, so I was right first time. So we don't need that there now. We know that all this part of the circuit is stable and working. So what we need to do now is to find out where the problem actually is. We're going to measure the voltage on the capacitor, this small capacitor here, yeah? I'm pretty sure this is the correct capacitor. We can just check that. If we look, there's a diode here. Cathode of the diode looks like it goes to this capacitor. Yeah, it's there. So we can say that goes to the capacitor here, yeah? The other end of the capacitor should go to the negative end of the large capacitor. I'll just show you on the schematic again. And it does, it goes to there. This is the negative end of the large capacitor, yeah? So what we're checking here basically is that we have the correct capacitor. So we've identified one end of the capacitor goes to hot ground, the negative end of the large capacitor. We can see this diode, in our case it's not coming through a resistor, it's connected directly to there. There could be a resistor in here, quite possible, but it doesn't matter. And you'll see the other end of this capacitor should go to the controller chip. So if we have a look on ours, if we had a data sheet, and this is the controller chip, this tiny little thing here. If we have a data sheet, we can look up which is the power pin. It's either called VCC or VDD. That is the power supply to this chip. And we can then measure. But we can probably figure this out without a data sheet. So we know the little capacitor is here. The negative end is going to the negative end of this one. So the positive end of that, connecting to this diode, should connect to one of the pins on this chip, probably directly. Could be through a low value resistor, but normally this is just direct connection almost, in fact, always I would say is a direct connection. So we can go from this end of the capacitor, and let's see if it goes to our chip. Can't see anything yet. I'm on the wrong place. This is the capacitor. So obviously it wasn't connected where I was. Yeah. So we can see, in fact, it goes to that middle pin. That is the VCC pin. So we know this is the right capacitor. And we can monitor the voltage across this capacitor, connect our bench power supply back onto here, set the power supply to 5 volts, which is the correct output voltage, and then turn the power supply on. Yeah. We know all the opto-isolator feedback is working, so the output of this should then be stable. Yeah. And the voltage across this capacitor should be stable. If the voltage across here is still changing around, then we're down to the fact it's either the diode, it's a faulty capacitor, which is the most likely, or it's a faulty chip. Okay? Or any resistor that's in that circuit in series. So that's what we're going to do. Voltage measuring across here, expecting about maybe 15 volts, and should be stable. We can switch it on first without the bench power supply, and I'm sure we'll find this is changing around, and when we switch our bench power supply on, it should stabilize. Okay, let's see what it actually does. So I've soldered a couple of wires onto where the capacitor is to make this easy. The blue one is the negative end, so we'll connect the black metal lead to there. The purple one is the positive, so we'll connect this meter lead to there, and then we'll power the power supply up. And what I'm expecting to find is that the voltage here is unstable, hence the fact the power supply is unstable. I'll just take the mains lead. It's not plugged into the mains yet, so we'll plug this into here. And anyway, my mains is actually connected via an isolation transformer over here, which is switched off at the moment. So the power supply is plugged in. I'm connected at the moment to the light bulb current limiter, so we can turn the power on, and let's see what's happening with the voltage supply to our chip. Well, it's all over the place, yeah? It's unstable as we expected. Okay? This is because the whole thing is unstable, the whole loop is unstable. Let's now connect our bench power supply to the output of this power supply. So we'll connect this onto here, and we'll connect the black lead to the negative of here. So we have the bench power supply. In fact, I'll just disconnect it one moment. We'll switch the bench power supply on. And I've set it to 5 volts. So that's set to 5 volts. We'll put our power supply back on, and then we'll apply the 5 volts to here. In fact, we'll do it this way. We'll connect the 5 volts to here. So we now have 5 volts on the output of our supply, yeah? I'm now going to switch the power supply on and see what it does. So this is our power supply plugged in. You can see the voltage on the chip is still unstable, and yet the output voltage is now stable. So this proves that the problem is the power supply to our little chip, and as I said originally, the most likely reason for that is the little capacitor next to it, which looks visibly okay. So I'm just waiting now for the voltage to drain away. I can take my multimeter, just disconnected the leads, and we can just check in the main capacitor to see if it has actually discharged now and is safe. So this is the negative end of the large capacitor here, and this is the positive end. Yeah, and it's discharged. 4 volts in it, nothing really. So let's now replace the little capacitor, and then let's see if our power supply is now stable. I'm sure you can see what we did there, but just for any beginners, just a little bit uncertain. We applied 5 volts to the output here, so we stabilised all this area of the circuit. We'd already tested this above and below 5 volts, so we know it was switching correctly. So we stabilised the feedback pin, and we then powered up and measured the voltage supply to this chip, which comes from this transformer, to see if it was stable. And it's not. The voltage supply to the chip is wandering around all over the place, which explains why the output going to the transformer is wandering around all over the place. But by fixing this, so we know this is working correctly, we know the feedback is correct, it's eliminated all this circuitry. This is now stable, and whatever is now unstable is where the problem is. That one, most likely. Could be the diode. If there's a Zener, it could be the Zener, it could be the chip, but most likely that one. I can take the 2 wires back off now. Okay. And we can remove this capacitor. We'll use a bit of braid, seeing as I don't have the vacuum desoldering tool switched on at the moment, and it probably take as long to warm up as it'll take me to do this anyway. So we have a bit of braid, okay, or the pin, okay, and with a bit of luck now this will just come out the board. If it doesn't just fall out, then a little bit of waggling will do the job. If you can see one of the legs, in fact both the legs are free, there's just a bit of glue holding it in place. So let's just, in fact I can see the glue, yeah, it's there. Okay, this appears to be faulty. They're normally about 10 microfarad. Yeah, 10 microfarad, 50 volt, very common. Sometimes I've seen 35 volts. It's a very common value. These are a value of capacitor you really need to keep in stock. And it should be a relatively low ESR one. Let's just test it and let's have a look to see how it checks. With a small-ish capacitor in value, in microfarads, the ESR tends to read a little bit higher anyway. But let's have a look. So we can just connect our emitter to it. It might be an ohm, you know, on a good one or so, but it shouldn't be like, well, actually, yeah, it's reading about. I'm actually not getting a good connection on it, am I? It's wandering around. Let's just short the leads together. Okay, we can hit 0. Okay, that's on 0. Now what's it reading? About 0.85. Let's take another one and see what that reads. I have quite a lot of these, just salvaged off things over the years. Probably satellite receivers with embedded power supplies, things which are basically obsolete, non-HD receivers, so they're not worth doing anything with. That's actually reading about the same. Let's have a look with the capacitance meter and see how these two are actually reading. Okay, here's the capacitance meter. We want the 20 microfarad range. Let's have a look at this one we've just picked up. Negative. That's reading about 10. What's this one reading? Negative. It's a little bit low. Let's just try another one out of my stash of salvage bits. I have quite a few in here actually. Let's see. 10 microfarad 50 volts. There's another one here. Let's try this one, or I'll even see if I can find a different coloured one actually. What we got is like a greeny coloured one, different make, 1050 again. See how this one's reading, and then we'll try one. We'll see whether or not it actually solves the problem. So here's the capacitance meter again. That reads a little bit low actually. I'm sure if I try a little bit more I will find one that's good. Another one, 10 microfarad 50 volt. The value isn't critical. You can put something a little bit different in, but you shouldn't go too much difference on it. Reading about the same, about 10 in that one. How's the ESR on this one? I wouldn't put a much higher value capacitor in, or much lower voltage, although probably you can measure the voltage about 15 volts on it. These are all reading about the same, and they're saying good capacitor if less than 47 microfarads. So let's try one of these, the one which reads the lowest, and let's see if it actually fixes a problem with our power supply. Here is our power supply. I've switched off and disconnected the bench power supply. We can just power this up, and let's see if we now have a stable output or not. No, it's still unstable, and I'm not totally surprised because that capacitor looked all right to me. So this has another problem, and it can only really be one of a couple of things. Either the chip itself has got some issue, or there's some resistors that are feeding the voltage from the winding on here back to there, which is basically got high resistance. That's about it really, or the diode which is in that circuit could have a problem. That's a bit unusual, and if it measures all right on a test meter, I'm sure it's going to be all right. So let's have a look to see exactly what is in the circuit. Okay, so we can see the diode is down here, cathode towards the capacitor. So let's have a look to see how this is actually connected on our circuit. I have the meter in diode mode. I'll just prop it up a little bit to get rid of the reflection of it. There you go. So the winding on the transformer is here, the secondary winding. This end will be connected directly to the negative end of the large capacitor, which it is. This end of the winding, and it will read a small resistance, probably reading 0, that's fine, goes to what looks like a resistor here. Let's just switch into resistance mode rather than diode mode. Yeah, so there's a resistor here, and that's reading 15 ohms. Okay, the other end of the resistor is going to the diode there. Yeah, so now go back into diode mode. The diode is okay, and you can see the diode goes directly to the positive of the capacitor, which is just right next to it there. It's got a good connection on it, and then from the capacitor we know already it goes directly to the chip. Yeah, so we could have a problem with this diode. I mean, it's a with this resistor. It's a 15 ohm resistor, and it's marked 15 ohms, and it reads 15 ohms. So I think it's likely it's probably okay. Let's have a look. Yeah, it reads 15 ohms. If it was a faulty resistor, you'd expect it to read high. I can change the resistor anyway just to be certain, but I really don't think it's a faulty resistor. I think that effectively this is drawing a varying current from the supply, causing it to wander around. Either that or both the capacitors I had fitted are bad capacitors. What I can try, as well as just change this resistor in case it's somehow breaking down, I can just try strapping a capacitor across this one. So this is a 10 and this is a 4.7 50 volts. So if I just tag this across the other one, just gives it a little bit more capacitance. Let's see if that actually stabilises it. If it does, I suspect maybe the other capacitor is not good as well. And I've just tested the ESR and a couple more, and all the ones I have basically read the same. So let's go and just put this capacitor across the other one. Okay, that's fastened on there. It's not shorting against anything, it's there. So we can try that, see if that stabilises. I will try changing the resistor. And if that doesn't work, the chances are the chip itself has got a problem, because there's nothing else in the circuit, and we've stabilised this side of it. So let's see what we get now. Put our voltmeter here. Just prop it up a little bit. There we go. We want volts range. Okay, volts. We can connect our leads. Negative, positive to the output. Okay, so I'm just measuring the voltage on the output connector again. And let's switch it on again and let's see what it does now. Well, it'll do nothing because I haven't connected the power lead, yeah? It's switched off at the moment on the power lead in. Okay, let's see if that other capacitor helps to stabilise this at all. Make a connection on the output. No, it's still all over the place. That made no difference. So really now we're down to either the resistor, the diode, or the chip. Let's see what I can find in my stash of bits. So as you can see, I didn't have a suitably sized surface mount resistor, but I've got a 15 ohm resistor, and I've effectively taken the surface mount one off and just stripped that onto the board. So this will prove whether there's a problem with the resistor, but I very much doubt it. You know, never say never, but I very much doubt it. That's not a normal failure mode for resistors, especially when they read okay with a meter. So again, let's just switch this on and let's see what output we have now. Well, again, it's unstable. You can see straight away. No change. I think basically I'm down to a problem with the chip, I have to say. I'll show you one or two other things why I happen to have this. So one of them is how to test if the pulse width modulator is driving the transformer. So with a power supply like this switch mode, you can't connect your oscilloscope probe to the high voltage side of the circuit. But what you can do, if we just balance it on something because of that resistor under there, yeah. If you hold an oscilloscope probe near to the transformer without connecting the ground of your oscilloscope to the power supply, you can see whether or not it's running. So let me show you how that works. I have my oscilloscope probe, so I say there's no ground, it's just literally the probe. Yeah, the ground lead I just click back here, it's not grounded. So if I hold this near to the power supply and turn the power supply on, yeah, you can see there, yeah, straight away that the power supply is actually running. Yeah. Strangely enough, for whatever reason, it's now giving us a steady output voltage as well. That's interesting. But that's how to tell if a power supply is actually running without connecting your probe to it directly. Yeah, you can see it there. For reasons better known to itself, it's now started to run stably. I wonder if it's when it warms up. I'll switch it off. Okay. I'll cool down the chip and we'll try again. But let's just flick it over. I'm going to cool the chip down. This is the last of my Mapling freezer spray. I need to get some more. So let's just... right, I've cooled the chip down with some freezer spray, as you can see there. Let's power it on again and let's have a look to see what happens now. Yeah. Put the power lead on. Yeah, it's unstable. Okay. Let's see what happens when the chip warms up. Let's in fact use the hot air. And let's just warm it a little bit. So I'm now warming the chip a little bit. Yeah, yeah, there, you got it. Yeah, we've got it. So we've basically proved that it's heat sensitive as well, and that is a semiconductor, and I'm as confident as I can be that is a faulty chip. Yeah, the only way to prove it would be to order one, but I'm not sure from the SMD code I can find out what it is. Having said that, let's have a look. There is the IC marked BTI. Yeah, looks like BTI SC. I had a quick Google, so I was basically looking for the SMD and then BTI and then the package size, which is SOT23-6. That's the actual package size. That's same size as a small outline transistor with 6 pins. So searching for that, yeah, I was searching for this, the code BTI and SMD code, and I think this is probably the right chip, although it doesn't specifically say how it is marked, but I think it's probably this one or some sort of compatible with this one. And the reason being is if we look at the chip, so it's 6 pin, we have VDD on pin 5. We already know ours has a supply on pin 5. So if we look at ground is on pin 1, and if the gate drive to the MOSFET is on pin 6, it's probably our chip, certainly to the point where we can actually order these and just try one. So let's have a quick look again at ours. We can check if the pin out of this chip matches that data sheet, and if it does, it's probably the right one. So this is the positive end of this small capacitor, the one that goes to the chip, and we know it comes to pin 5 VDD. So if our chip matches that data sheet, ground, which is here, or the end of the large capacitor, there, yeah, that's ground, would go to pin 1, and it does go to pin 1. And then lastly, pin 6 would go to the gate of the MOSFET, which it doesn't directly, but it looks like it goes to a resistor here. That one. It goes to that resistor, and the other side of this resistor goes to the gate of the MOSFET. The MOSFET being in here, and this being gate, drain source, or gate source drain, it's always pretty much gate on that end. So the pin out of that chip matches the description in the data sheet close enough that I'll be confident to just try one of those and see if it works. I wouldn't have those in stock, but we could have a quick look to see how much they are. So here is the chip on AliExpress. It's €1.02 plus €1 shipping. I may as well order some of these and then I have them in stock. I normally find if I get something like this that's faulty, if they're inexpensive, I usually just order some. I can use it to fix this power supply. I have 9 more of them, might be useful at some point. I'm more interested to repair this just to prove the point, but I think the freezer spray already did that. Let's have a look at number 6. This is a 12 volt 2 amp, and we have fuse, 2 high voltage capacitors, and this is the filter coils in between, the double bobby, not a transformer, a filter. This is the main MOSFET, the switching MOSFET. It may have a I don't see a control IC underneath. This could be one of these self-oscillating types, or the control IC could be down under here for that matter. We then have the transformer. This is the output side. The capacitors look okay. You can see the division between the high voltage and low voltage side. This has an opto isolator down in there, and then this is the diode, the rectifier on the output, and this is a heatsink attached to it. That's what we basically have. Again, we have 2 or 3 output capacitors and an inductor as well, probably in between the 2, or you've got 2 in parallel, the inductor and 1 more. So that's basically what we can see in this one. The only thing I don't see is a control IC, which could be under here. there's not a lot of components on this side. I've not seen many transistors, so I'm not sure this is a self-oscillating one either. Let's plug this one in and let's see what the problem is with this one, and then we can take it from there. I have the power supply plugged in, the light bulb's here. We can switch it on, probably nothing will happen. A little flick and it went off. So that means the thing powered up, or at least the capacitor charged up, the main capacitor. Let's see if it actually is generating any output. So this is the output connection. Oh, this one's actually working. Oh, interesting. Okay, so that's an actually working one. I'm not sure what the problem was with it previously, but at least it indicated the fact that it powered up. You saw the light bulb kind of flick and go out. I think I'll put a bit of a load on this one, so we'll switch it off. The output voltage should now eventually decay away, and this should be discharging the main capacitor. I wouldn't always trust that. So yeah, voltage is dropping down now. It's still there, 12 volts. Let's connect our resistor to this. So we know we can use the 20 ohm 5 watt resistor. Okay guys, this is the next one, and hopefully now you should be able to recognize pretty much everything we see here, I would think. This will be a fuse on the input. We have two large capacitors on the high voltage side. I can't easily see the markings, but I'm pretty sure these are both 400 volt capacitors. We have the two windings on a bobbin, not a transformer, but filter inductors, possibly between the two capacitors or one side or the other. This looks like either a current sense resistor if it's a low value, the startup resistor if it's a high value, and I can't easily see its markings, a bit vague. Maybe brown, grey, black, which would make this 1.8 ohms, that'd be a current sense, or an inrush resistor like we saw on some of the other ones. That may well be a thermistor, which is like an inrush resistor. So it starts off at a relatively high value, maybe 10 ohms, and as the current passes through, it warms up and the resistance drops. So it's just to stop an initial surge of power. This heatsink only has one device on, which is the main switching MOSFET. I can see 400 volts marked on that one now, and I can see 400 volts marked on that one. So we've identified all that lot. This capacitor will be to do with the startup circuit, and I would have thought, yeah, so that capacitor down there will be the one effectively is initially charged up by a high value resistor from the 320 volts, and then this diode takes over from a secondary on here. What we've seen before, yeah. There's probably some stuff on the other side of here. Opto isolator, TL431 voltage reference, or something equivalent to that. AZ431, just the equivalent. And then we have some capacitors on the output. That's the output diode, the rectifier diode. You can see inductors, capacitor, capacitor. So you've probably got some capacitors after the diode, maybe these two in parallel, and then inductors and the other one, or maybe there's 3C, you know, so you've got effectively one capacitor, one inductor, another capacitor, another inductor, another capacitor going to the output. So that's what we have here. Let's see if we can easily lift this up and get to the other side of the board. Yeah, it's coming out. Something went crack. I think it's where the actual power connects to it. Ah, yeah. So this is going to be the controller chip. 6 legs, basically like the one we just saw on the previous power supply, but one that is basically looking like it's faulty. I may have actually, that crack, I might have actually broken the connection on one of the inputs down here. I'm not sure. But let's try and power this up and let's see what this one actually does. So I've just put a bit of tape around it temporarily. I'll just have to get an adapter from the English to Spanish power socket, and these are the output wires where we can measure the voltage. I have that plugged in. I'll just move the camera around so you can see the light bulb on top of the variac, and we can just switch this on. Let's see first, before we measure the voltage, what does a light bulb do? Well, the light bulb does nothing, like there's no current gone into it. Is there anything coming out of it? So just go on to the output connection. No. So this is like it's completely dead. It's not drawing any power. Nothing's happening. I'll just switch it off. We can have a quick look and just see if there's a short on the output. Ah, there may still be some voltage in it. This is a short circuit output. That's one of the first problems with it. Yeah, the output is short circuit. I mean, it's switched off, so I can just short these together just in case a little bit of residual voltage in the capacitors. Let's try. Yeah, that's got a short circuit output. That doesn't necessarily explain why the light bulb didn't come on, because you'd expect if the power supply is effectively trying to run, the bulb would come on fairly bright. So let's open it up again and let's have a look. We're seeing a short circuit on the output, and this is a fuse on the input. There's a good chance the fuse is blown. So let's take a look at that first. We're on continuity range. Has the fuse blown? Yes, it looks like the fuse has blown. So there should be no voltage in these capacitors, but we better check that. So let's see if we can lift this open and see where those capacitors actually are. They're kind of down in here. I'm most likely going to end up breaking this to get it off. Yeah, but I'll probably actually unsolder these in a moment. I can see now, I think, the connections from those large capacitors. They're kind of like running in this direction. So it looks like that's the end of the filter. So the first capacitor appears to be here. Can you see it there? Let's go across this on volts range. With a blown fuse, there should be nothing here. Well, actually, we have 7 volts there. You can't see the meter, can you? We have 7 volts there, so that suggests the fuse isn't blown. Otherwise, why would you have any voltage in there? Yeah. That's one of the capacitors. The other one's a little bit further back. I can see it. It's kind of these two. So from there to there. Yeah, I read about 7 volts again. Yeah, it's dropped down now. So that suggests the fuse is not blown. Maybe I wasn't making a good connection on the fuse at this end. I tried to measure it. Let's have another look. So where's this fuse actually going to? Well, I can see one end of the fuse is there. Okay, just there. And the other end is just here. Let's see if we can measure this fuse again. Continuity. You'll hear it bleep even if you don't see it. One end of the fuse. This is very strange because this fuse is reading open circuit. It's definitely reading open circuit, and yet I'm seeing some voltage in these capacitors, and that doesn't really explain how that could get there. Let's see if I can unsolder this thing so we can get in at it a little bit easier. And there wasn't much voltage, so this is not really a problem. Let's get into this thing. Not easily. Oh, I see. They come through. They come through here basically. That's what these blobs of solder are doing. You can see these big blobs of solder here and here. The effectively connecting them together. That's what it is. So to take this off, we need to unsolder these. Let's have a go. Yeah. So we have the 2 bits still in there. This one's snapped off. We could solder wires on and bring them through, but the chances are I probably won't use this. It's very messy. I'll probably fix this and then keep it as a spare power supply, useful for my own projects, and to put internally in a project case enclosure. Okay, so we see where the power comes in. Now let's have a good look at this fuse. Continuity range. One end of the fuse is here. The other end goes down to here. Open. Is that a fuse? Oh, it is a fuse and it's not there. It didn't make sense. It was like it was directly across the mains. One end goes to here and one end goes to here. Well, the fuse is certainly open circuit, so that's a bit of a mystery, isn't it, how we could have ended up with voltage in the capacitors. Let's unsolder this. I'm only assuming some sort of leakage current somehow was getting a little bit of AC through, so the capacitors were effectively charging up. I mean, one end of the bridge rectifier would be connected effectively to the AC on live or neutral. Although I have no live and neutral because I have an isolation transformer, but I don't know, it's a bit strange. I got some voltage in there, even if it was just a small amount. Whatever this solder is, it doesn't like to. Oh, my soldering iron has gone half to sleep. Try that. That's why the solder didn't want to melt. The soldering iron had gone down to 200 centigrade by itself. Stick that on there. Get hold of this end of the fuse. That's out. Other end of the fuse is over here. Yeah, got it. Come on. Fuse, which is reading open circuit. Let's check you again. Fuse. Yeah. Okay, so that is definitely an open circuit fuse. What rating is it? I mean, this is a low, at the end of the day, it's like 20 watt power supply. So this, you'd expect to be quite a small fuse, maybe an amp. I don't know. We'll see. The last one we looked at was a 2 amp. And this one's a little bit fiddly to get this stuff off it. At least I've got fuses of the right physical size to fit in this, I think, most likely. Yeah, looks like a 20mm fuse to me. And this heat shrink stuff doesn't really want to give it up easily. Oh, I'm going to the capital Las Palmas in a couple of weeks. For a couple of nights, and I'm going to see a band in concert. There's a big concert, it's almost sold out, and it's the Pet Shop Boys Dreamlands tour, the Greatest Hits World Tour Live, and it's on at Las Palmas Arena in the capital, and I'm really looking forward to that. Don't know if any of you guys would be into that sort of thing, but I was looking up Neil Tennant, the singer, is 72 years old now, so I think this is probably like the last chance you're likely to get to see them live. So It's at the arena, 10,500 people capacity, and I'm looking forward to that. While I've worked on about that, I've got the fuse out. Let's see what rating it is. There is our fuse. It's rated 2 amp. So that's a 2 amp fuse. Let's replace that, but before we do, let's look for the short circuit on the output. Switch mode power supply with short circuit output. Almost certainly the fault will be the diode, the rectifier diode. It's by far more likely to be that than anything else. We want resistance range, we have the 2 wires, and we definitely have a short. So we'll unsolder the diode, which is attached to this heat sink, so that's probably mounted over here. This one I might be able to actually get it out by just undoing this screw. It's easy to get at for once. Unsolder the 3 legs of the diode and take it out. So let's put the vacuum tool on, and while that's warming up, let's see if we can get this screw out of here. That's a bit too small. Try this one. That's the right size, but the whole thing's just turning round. What else do we have along those pliers? Okay. Yep, that's doing the trick. So that's our diode unbolted. Yeah, it's free from the heatsink. So we need to get some leaded solder. 3 pins, so it'll be probably a double diode. That's what they normally are. Double diode, common cathode is normally what we will find in these. And it's probably a Schottky diode as well. So that's the diode. Let's get the. I can hear a bit of air coming through it, but I'm just not sure it's totally clear. So, and it looks like I need a new tip on this anyway. Yeah, you can see the tip's kind of like broken. I have some new tips, but for this time I'm sure we can get away with it. Waggle it about. It looks like it's unsoldered. Middle pin, not unsoldering very easily. Yeah, need a bit more leaded solder on this, I think. Okay, try again. Middle pin. When they get like this, so they're not easily going to unsolder, just get the soldering iron as well and just give it a bit of help, yeah, so we can just warm it up with the soldering iron. And now I'm sure it will come off. I might have got both at once. Yeah, I actually got both at once. Let's see if that'll actually come out now. Again, just give us another clean after use. Yeah, still a little bit blocked. I'm going to, before I use this again, I'll clean all the solder out and put a new tip on it. I ordered some new tips about a couple of months ago, figuring out that it was going to wear out fairly soon. So the best time to order some replacement tips is when you don't need one, because then you'll have it when you do need it. Okay, yeah. That's free. Let's get it out if we can. Yeah. There we go. One diode, I would say. Does it have a part number on it? Let's get a torch. There are some markings on it, but they're not easy to see. Let's see if it's short circuit. the meter onto diode mode. Here we go. Let's see. Oh no, that reads okay. So this diode looks like it's okay. It's a bit fiddly because the legs are not very long, but looks like we don't have a short circuit diode in this case. Yeah, Schottky diode. Schottky diode. So where's the short if it's not there? Once again, let's go across our test leads on the output cable. Short. So where's that? It's very unlikely to have a short circuit capacitor, but there's not a lot else down here, to be quite honest. There's not much else that is really there. Actually, two capacitors, 1, 2, an inductor, a resistor, but that's not going to be short. Let me just get where you can see the meter there. So there's a short. There's a short in the cable. Well, according to this, there isn't a short at that end of it. There's a short at this end of it. Well, that makes no sense, does it? It's a piece of cable. So there can't be a short at one end and not the other end, can there? Really? Can there? Yeah. Can there be a short at one end of the cable and not at the other? Oh. I mean, we do have a short. We had to have a short, so there's a short on here somewhere. I mean, we can take the cable off, but I don't really think that's anything to do with the problem, but let's just get rid of it anyway. Yeah. Bit fiddly because of the glue that's on it. Doesn't make it easy. Let's try again. So that's melted. It's just the glue that's holding it in place. Solder's melted now. It's off now. I'm just wondering if it's like broken behind this strain relief here. Possible, because it's unusual to find a short on here. And we still have a short. Very strange. It's not like a solder bridge somewhere, is there? Can't see it. I can't see this. Looks like a track. That's just a bit of like red gunk, I think. I don't think it's anything other than that. We have to start pulling these capacitors, but okay. The first time for everything. Oh, there's another diode down here. There's another diode there. I wonder if that's short. That's more likely. Let's have a look. Where is it? It's across here. Capacitors very rarely go short circuit. I'm not saying never. I'm just saying not very often. That is more likely to be the short. The diode. Diodes are much more likely to go short than capacitors are. So let's take that one out and see. Maybe this wasn't a diode. Maybe this was a voltage regulator. No, it reads like a Schottky diode. It's a Schottky diode. So we have the 2 pins of the capacitor. Then just inside of that, the 2 pins of the diode. So let's get a bit of a solder on this one and this one. This is very tough solder to melt. Well, let's get in with the desoldering tool. Let's try to take this diode out. There. I really don't know what this solder's made out of, but it doesn't want to melt. Again, we'll try the two together. That end's free. That one isn't. Nasty, nasty stuff this is. Nasty, nasty stuff. Again, come in with some fresh leaded solder. And again, come in with it. Vacuum desoldering tool. That's better. That sounded like it had it. Okay, let's see if that comes out. And it's reading short. Good guess, eh, guys? So that's our problem. Where is this connected in the circuit? I'm just wondering if this is actually a rectifier diode or a Zener diode. It's a Zener diode. Can you see the symbol there? ZD1. The only thing I can think this is like a 13 volt Zener or something like that. It'll be wired across the output, basically, which is why it's reading short. And it's there as an over voltage protection device. That's what I think that is. So initially, I think I'll actually leave this out, replace this rectifier, power it up and see what output voltage we've got coming from it. This is quite a chunky diode. I'm not sure. I have some 1 watt Zeners, but I think they're smaller than that. Yeah, these are my 1 watt Zeners. Oh no, maybe they're the same. Maybe they're the same. So I would suggest that whatever Zener goes here is just a bit more than the output voltage. It's there for protection. Yeah. So now we've taken that out, I think we can say with good confidence as the short circuit will be gone. So let's have a look. Yeah, there's no short there anymore. So we can put the cable back on. We can put our other rectifier back in. But before we do that, let's see if there's any shorts on the primary because the fuse blew. I mean, quite likely that would just cause the fuse to blow, but it's worth checking if there's any short circuits around the MOSFET. No, not there. Not there. Not there. If we measure across the main capacitors, it's like a diode that way. Is there a short circuit bridge rectifier diode? Let's have a quick look. That one reads like a diode. That one reads like a diode. That one reads like a diode. And this one the other way around. No, they look okay in circuit. So we'll replace the fuse, we'll refit the rectifier, we'll leave this off for the moment and we will see if it powers up. The Zener diode is actually connected directly across here. From here, Zener diode. A bit awkward to draw because I haven't got it very flat, just making life difficult for myself. It goes like that. Okay, so the idea of this Zener diode is that normally it just doesn't do anything. So if we put, say, a 6 volt Zener in here, as long as the output stays below 6 volts, in other words the regulation is working, nothing will happen. If something goes wrong with the regulation and the output goes above 6 volts, that will switch on and effectively short out the output and blow the fuse. So that's what it is, and the idea is it acts faster than a fuse could act to protect whatever device you're powering with this. So that's what that is about. I'll attach a couple bits of wire on just to connect the mains to this, and then let's power it up and let's have a look to see if it's working now. I'm set to DC volts on the meter. I have the light bulb in circuit, so I'll just move the camera initially. You can see the bulb up under here. So it should just flash once, but again it'll stop anything particularly nasty from happening. So let's see what it does. Yeah, it flashed once and went out. That's good. So now we can have a look to see what voltage is coming out of our power supply. And we have no output voltage. This is where you could end up with this situation of having a high voltage charge into the main capacitors. So let's have a look. I've switched the power off now. Yeah, this is about 80 volts, so there's definitely power getting into these large capacitors. So it's dropping down to 40. If I switch it back on again, you will see that the capacitors charge up to about 325 volts. And we switch off, and that voltage is dropping away. But it takes some time to drop away. This is why you have to be careful with power supplies. It is dropping away. That suggests something is drawing power from the capacitor, but there might just be a resistor in the circuit somewhere intended to drain the capacitors. It's likely the power supply itself never started. So we need to figure out what is wrong with this one. With a power supply that doesn't start, but there's voltage getting into the main capacitors, the first thing to check is whether this controller chip has any power. Now this is a little 6-pin device, and it might be very similar to the last one. So here is where the startup capacitor goes. That's this one. Yeah, this is the startup capacitor. So this should be charged up via a high value resistor, either internally or externally. If you look at the capacitor, this leg actually goes to here and back to here, and this is the negative end of the electrolytic. So we have bridge rectifier, we have one electrolytic, then we have the two filters and the second one. So you can see that there. This is the output from the bridge rectifier going to one capacitor. Yeah, so that's the two cathodes or two anodes. This is the other two. That's the capacitor across them. These are the coils. And then from this side we go to the other capacitor. Yeah. So from here to here, from here to here, and this is the other capacitor. The negative here goes to, well, we can see where it comes from. It comes via this coil from here, from this end of the bridge rectifier, yeah? These diodes. And then the other end comes via the coil where we just looped, yeah, through the coil to these two diodes. So that's all there. So this is the negative end, and that goes to this end of this capacitor. So this is hot ground, and then the power supply to the chip will be on this capacitor. So you can see the capacitor goes down this way to this chip, and it's probably the same as the other one, so it's probably pin 5. Yeah, there's pin 5, in which case this is pin 1. This is the same as the last chip, and that will go to the negative end of the capacitor, hot ground. Yeah, it does. Where the supply comes from, it comes to this resistor here, which I'm sure is a high value resistor, in series with another high value resistor, and it looks like 3 of them. Yeah, or some. Actually, these might be current sensing resistors. Oh, what was this here? This looks a bit messy, doesn't it, what we got here? That's just dirt. We need to get us under the magnifier, the microscope, and let's have a look to see what we have here exactly. Okay, so this is the positive of the capacitor. This goes to hot ground. This is hot ground. It comes here, yes, through a 750k, is it? 750 and 30, 750k, another 750k to here. So effectively that's 1.5 meg in series. And then this is going to be, yeah, the positive side of the main capacitor there. Yeah, you can see it. But we also have something here as well, or we did have. And this is possibly related to what the problem is. Let me get something to brush that off with a little bit better, and let me have a look under the microscope myself. Okay, so there's definitely something going on here. Let's give that a bit of a... Right. So that's a 0 ohm resistor. This either never existed or it's a kind of vaporized resistor. It looks like some liquid or something's got inside this somehow. And this appears to be what there's a problem here. Let's scrape a bit more of that off. And let's see what we've got. So that's just gunk. Is there a broken track here? Or a corroded track here? All this is a bit corroded, to be quite honest. Bit more ISO. Well, it's a bit cleaner now, but something obviously has got into here. Let's see if we can figure out what that actually is. Well, we can see. This is the positive end, so this is the 320 volts. It goes, I'll just put it onto resistance mode, to the first of the 750k resistors. That then should go to the second one, reading 750k. And it doesn't, it reads like stupidly high. Let's go across the resistor. Okay, 430k. Yeah, about right, 480, 500k. I mean, it can read a little bit lower than the other. Yeah, about 1.1 meg it read. It's now charging a capacitor or something, but it shouldn't read higher than the value of the resistor, about 530k. Some capacitor charging somewhere. Okay, so that's probably about what you'd expect, and that then goes to this capacitor. Do we have a connection to here? Should be about 1.5 meg, I mean 750k twice, yeah, it's reading about that. Across the capacitor should really be a high resistance, it should be very high resistance. Otherwise, there's a problem with the chip or something like that. Yeah, overload doesn't. So that's basically reads open, that's what you'd expect. 28 meg, 17 meg. So they read okay, so that would suggest we're getting power to charge this capacitor up. It then goes the same power. These are 184, 18 and 4 zeros, so 180k, 3 of them in parallel is basically a third of 180k, which is about 60k. So that's what you expect to read here. Yeah, about 60k. Just goes to show how good ohms all is, isn't it? Useful. That 60k then comes to here. It doesn't go to there. This is a 0 ohm resistor. And this reads open circuit. That's a 0 ohm resistor, yeah. That you'd expect to read So that's open circuits, that's a problem. It's whether or not there should be a connection from here to here. And I think it's likely there should be. I'll have to scrape away a little bit more at this and have a look to see, probably under the microscope again, exactly what there is. But what we definitely have, without a doubt, is an open circuit 0 ohm resistor here. Let's try this, it's a little bit sharper. I would have to say, in my opinion, what's happened here is that the track is effectively blown away completely from here to here. That doesn't join to there, okay, so that does not join to there, that's for sure. There's a gap there, so this doesn't come across. But I'd imagine that is probably supposed to be connecting to there, and this 0 ohm is supposed to be connecting to there. And I think that's all disappeared. I think something, whatever probably blew the fuse, has also caused this to go away. And it's very hard to determine what that's doing, but looking down here, there's a high voltage capacitor and another capacitor down there, and a diode. So the diode comes in to here. Yeah, that's the end of the diode. That's the 0 ohm resistor, and then this is the capacitor. This one, yeah. And then that's the other capacitor not connected directly in. I think we need to fix this. We'll try to unsolder this and then try and clean this up properly, but I'm pretty sure we need to fix that, and that's got a lot to do with why it's not actually starting up. Yeah. Now I've cleaned up this part of the PCB, we can clearly see that the track here is burnt through. There, okay, this is one end of the 0 ohm resistor, the other end went to here, and from here we have a connection to a component. If we look on the other side, you can see, just move this out of the way, that is a diode. So it's the cathode of a diode, and the anode of the diode comes down towards the MOSFET. So that's what we have. This point is the positive of one of the 400 volt capacitors, which have 320 volts DC in them. So this point is, when it's powered up, has 320 volts DC, and this end is the negative of the capacitor, which is effectively hot ground, which is our 0 point, so we can call this ground, hot ground. So let's look at the circuit. The power comes into the capacitor, and from here we have two lots of resistors. So these are marked 7503, which is 750 followed by 3 more zeros, so that's 750 kilo ohms, 2 of them in series, 1, 2, and that comes down to here. And this, if you look on the other side again, is the capacitor, which is in the startup circuit. So these are the high value resistors that initially charge this capacitor to start the chip running. And we can see the circuit, we can just check this out. So we know the 2 resistors were okay, I measured them before, but I'll do it again. Let's go to resistance mode, one moment. So the 2 resistors are here, and they should read about 1.5 meg. It might read a bit different because of capacitors charging. Yeah, it's charging up. But it's coming down. It will go to about 1.5 mega ohm. So we can say that these resistors are okay. Yeah, it's getting to there now. So those resistors are okay. From here, we go to the capacitor. Okay. I'll put it onto continuity. You can hear the bleep now. So there we have contacted there. And then from the other side of this capacitor, this is the negative side of the startup capacitor. This will, of course, go back to the negative of the main 400 volt capacitor. So that's our ground. So from here, we should go to the chip. The other one was pin 5 on the last power supply. So that's, yeah, pin 5, they're saying. So that's power to the chip. And then from here, there should be, if it's the same layout as the other one, 0. Yeah, coming back to hot ground. But let's go back to these other resistors. So these are the ones marked 184, which is 18 followed by 4 zeros, or 180,000. So each one is 180k, all in parallel. So we read 60k, and we measured that before. We know it's 60k. There we go. Yeah, 60k. And that then should go to the 0 ohm resistor. Well, the track's okay, so we do have a connection to here. And that should connect to here through a 0 ohms, which obviously is gone. And then we have a diode. And the other end of the diode quite clearly goes back to the drain or source, the middle pin of the MOSFET. Okay. What else do we have here? We have something else here. So we have, yeah, down there a high voltage capacitor, that one. I can see it. That's here. The other end of that capacitor goes to 200 ohm resistors in parallel. So that's 10 plus 10, 101. It's not 101 ohms, it's 10 and 10. So 100 ohms, 2 in parallel is 50. And that comes back, look, you can see it comes back to, through the resistors, let's go to the other side, comes back to the 320 volts on the large capacitor. It's down to it, yeah, it's there. Okay, so we have two things we can look at. First of all, is what is this circuit doing? What is this diode doing that goes with the positive towards the 320 volts via some resistors, and the, say, positive of the cathode, and the anode is going to the MOSFET. Well, to understand what this is doing, we need to go back and look at the water wheel again. I hope you watched part 1, otherwise you won't understand the water wheel. But I'm assuming you did, so let's go back to that and I'll explain what this circuit is supposed to do. This is the water wheel. Remember this? So the pump is pumping water, the wheel starts to spin and the water comes through and completes the loop. Before the wheel is spinning, we have a narrow section of pipe here that lets some water through. So initially, pump is on, a little bit of water is coming through here, a little bit of current, yeah, and the water wheel starts to spin due to the pressure here. Once the water wheel is up to speed, all the current is pretty much flowing through the water wheel and practically nothing is coming through here. So basically, in a little bit more detail than before, initially we have a high pressure here caused by the pump, yeah, and we have a low pressure on this side caused by the narrow section of pipe and the fact the water wheel is not spinning yet. So the pressure, if you like, the voltage across the water wheel is high, but there's no current flowing. Yeah. As the water wheel spins up, it gets towards full speed. And at the point it's at full speed, if you think about this, the pressure across the water wheel is very low. So there's practically no pressure across it because the water just flowing freely through here. Yeah. So at that point, effectively, the pressure at both ends of the water wheel are equal. Yeah, the pressure at both ends of this little pipe are equal and there's no water flowing through here. It's all coming through there. Now we switch the pump off. The water wheel is heavy, it has inertia, it keeps on rotating, it can't just stop. So now the pump's off. The pressure is here. Yeah, the pressure is the water coming out of the water wheel. This is the high pressure. This point now is low pressure because the pump isn't running. And look what the water is going to do. It can't flow back through the pump because we've closed the valve. Yeah, the pump is off. but it's got to go somewhere, yeah, and where it actually goes is back through this narrow section of pipe and back into the water wheel. It completes a loop this way, yeah, through the narrow pipe. Okay, that's where the water's going. This is narrow, so it restricts the amount of water flowing. So it takes a while for this to spin down, yeah? It can't just stop. All the water can't just come through it. At this point, this end of the pipe is now the positive pressure, high pressure, positive voltage, and this is the negative. And if you look, the current, when the pump was running, was flowing through the pipe that way. When the pump is off, the current flows through the pipe that way. It's reversing, yeah? The polarity is reversing, the current is reversing. Let's go back to our circuit. And just before we do, imagine if this pipe wasn't here, yeah? Or was restricting the flow too much. What would happen? This would be spinning round, a lot of force, yeah? That pressure's got to go somewhere. We have an unstoppable force against an unmovable object, the valve, yeah? It's either going to burst the pipe or it's going to break the valve. It's got to go somewhere, yeah? It can't go nowhere. So that pressure when the pump switches off has to go somewhere. And the same applies to our circuit. When we switch the MOSFET off, we suddenly get a high positive potential here compared to here. Now, this end is stuck at 320 volts. It was 320 volts because the capacitor's charged up. That doesn't change. That's still 320 volts. But we've now got a higher voltage than 320 volts on this end. And that could be, for instance, like 600 volts, yeah? 640 volts, something like that. That voltage can be too high for this MOSFET. So where the pressure has nowhere to go, it's likely to blow the MOSFET. Yeah, the MOSFET will go short because it can't handle that pressure, that voltage. So this is where our diode comes in, the one we've just seen. I'll have to just draw it somewhere else. I don't have the space for it here. But this is where our diode actually goes. We have the inductor coil and we have the MOSFET going via a current sense resistor to hot ground. Okay, this MOSFET is off. This end has 320 volts on it, and this end, let's say, has now 640 volts on it. A force from the collapsing magnetic field, yeah? So from here, we take a diode this way round, yeah? Reverse bias, but remember now this end is more positive than this end. From this diode, we could just go back to here. In our case, it's actually going through 3 resistors in parallel, yeah, to share the current to there. This is effectively the 3 times 180k, 60k. Yeah, it's going to there, and it's also going, draw it from here, via a high voltage capacitor, yeah, via another 100 ohms, no, it's 50 ohms, it was 200 ohms in parallel, yeah, it was 2 of these in parallel, and from here it's also going back to here. So this network effectively relieves the pressure. This is your pressure valve, yeah. This pressure is called back EMF, and this happens with any inductor, whether it's a transformer, a relay coil, anything that's an inductor, a solenoid, a motor. You'll see these diodes, and that's what they're doing. This little thing with the capacitor and the 50 ohms is called a snubber network. You can go and look up the detail, but basically, initially, a good chunk of current will flow through this till the capacitor charges. Basically, that's what's happening. So that's where that pressure is going, yeah, as the water wheel spins down. And in our case, we've got in here a 0 ohm resistor. So these are all connected together, and we actually have a resistor in between them, which is a 0 ohm link, and that link has gone open circuit. And for that matter, the track's blown as well. Yeah, the whole track's gone open circuit. So that's been caused by something. It's got to have been caused by a big power surge. Yeah, which is almost silly. If you get a big power surge, you'll also get a lot of output voltage, which will be what's blowing this as well. The Zener diode makes me strongly suspect that this chip internally, in our case, is actually driving a separate external MOSFET with a resistor. But I think something bad happened with this chip. Put a lot of voltage on here, pulled a lot of current through. This probably went open circuit. This has still got to collapse the magnetic field. There's a very large magnetic field in it now, so that's going to come back up through here. It's blown this, it's blown this, and it's induced into the secondary, and it's blown that. How feasible does that sound, guys? Now let's see if we can fix it. I wonder if this chip has the same pin out as the other one. So this is the MOSFET. This would be the gate. That's going to looks like a 22 ohm resistor here. That's one end of it. Yeah, 22 ohm. Again, they might like 220. That's not 220. That's 22 with 0 zeros. In other words, just 22. That's how you read these resistors if you were ever a little bit confused by it. So 22 ohms. And then from there it should go to pin 6 if it's like the other one. Yeah, it does. So this chip has the same pin out as the one we had on the previous power supply, even though it actually has a different part number marked on it. So if we need a chip, well, I've ordered them for the other one. So we can have a look at this. We can check if the chip is running, we can check if it's got power. But before that, let's have a look at the other circuit. We can easily replace the 0 ohm resistor with just a piece of wire, so I can bridge a bit of wire from here to here to here. They should all be connected via 0 ohms. So you put a bit of wire in there. Then let's remove the MOSFET and just test the MOSFET to see if that's okay. And if it is okay, then let's see if this chip has got any power. This will do the job nicely, just a stiff bit of wire. We get a bit of a flux. So we're going from here to here to here or here basically. Okay. So get a bit of solder. Should do. And take out a piece of wire. Okay. Okay. There we go. So we fixed that problem. Now, it's possible because of that effectively being open circuit that there might be some damage to the MOSFET, so it's definitely going to be necessary to test that. I can't easily get at it without removing the entire heatsink, so the whole thing's going to have to come off. Okay, I have it off. There was just one support which was actually there. I was sure there would be. Let's see if this MOSFET's any good. And let's see what it says. Yeah, MOSFET's okay. That's good. So we can put this back in, and then we'll power it up with a light bulb in series as we did before. And let's have a look to see if the controller chip has any supply voltage. There we go, all fitted back on again. I doubt very much this would stop it from powering on. It may cause the MOSFET to blow, but obviously that hadn't. So we'll measure the voltage across this capacitor and we'll see whether this chip's getting some supply. Easiest way to do this is going to be to tag a couple of wires onto it. You don't want to be slipping when you're on these sort of high voltage circuits. I mean, if you're feeling confident, then just stick your meter probes on, but for the amount of time it takes, I'm happy to do it this way. Okay, that's one. This one's hot ground, so it can go anywhere. Go here. Okay. So we have the two wires on, and then we'll power it up. Obviously, if we've got no supply here, then it can't start anyway. Okay, I'll put the other camera on the light bulb, which is under there, just in case anything interesting happens, and we'll switch it on now. Ah, you see that? Right, this is how I described in a previous video. So what's happening here is the controller chip has got power, but once it starts to run, it drains the power away because the high value resistors cannot continue to provide power there. So I think what it's doing is it's effectively, and it is switched off now, the capacitors are just discharging. It's trying to start and over again, but not managing to start. We can prove that actually by measuring the voltage on the output. So let's have a look to see if our power supply has any output. Just clip the leads on here, just as easy. This is the output. Okay, so we'll switch it back on again and let's see if we see any output. No, we don't. So there's no output, even though this gets a supply effectively. What we'll do now is we'll have a look to see if the transformer is trying to start up. So we can use the technique we used before, put the oscilloscope probe close to the transformer, and let's have a look to see if it's trying to start. If it's not trying to start, then I would say we need to replace the chip, the controller chip. So we'll take the oscilloscope probe and just hold it close to the transformer as we did before. You can see a little bit of interference there if you like, and we'll switch the power on. Let's see if this is actually trying to start or not. No, there's just some very low frequency pulses there, yeah, and we're talking probably mains frequency, I would say. We're on 2 milliseconds per division. 1, 2, 3, 4, 2, 4, 6, 8. Yeah, that's double mains frequency basically. So it's not trying to start. There's some problem going on with the controller chip. We know the MOSFET's okay. We know there's no short circuit on the output. It's just not actually trying to start at all on this one. The good thing about that is the controller chip seems to be compatible the same as the previous one. We can have a quick look at the markings on it and just see if we can find that out. There we can see the controller chip. It's marked 63719. I'll just have a quick look so I can find a relevant datasheet for this. Yes, that seems to bring me back basically to the same chip, although I can't say exactly, but because the pinout appears to be the same, I'm fairly confident it is the same chip. So I've ordered them from the other power supply and we can have a go fixing this one as well when those parts arrive. Okay guys, I was going to look at 5 power supplies on this video, part 2, and cover some topics which I didn't cover in the first one. And just by chance, the 2 of the 3 power supplies I did look at actually allowed me to do that, and they both need the same part as far as I can see to get them working. This video again is getting much longer than I expected, so I'm going to propose that we end this one here, and if there's enough of you guys interested, then we can look at these 2 on another video. But I do believe we've covered all the topics we need to cover. for the video, all you need to know about power adapters to fix stuff. And I hope you guys agree, and now you feel confident to work on these power supplies with a good likelihood of actually repairing them. Okay guys, let me know about these in the comments below, or anything else that you don't feel was covered in the 2 videos we've made. And I will see you all soon on another Learn Electronics Repair video. Ciao for now guys.